Okay, great. Welcome back. Second session, last session for today. We ended the previous session at the discussion of state space explosion and whether or not model checking is useful in the light of state space explosion. And the answer was yes, because of the, not because of the small scope hypothesis, but the small scope hypothesis says that even with tiny models, we find most of the issues. I believe I'm only aware of one specification where a model of 3 nodes did not exhibit a bug, and the bug only showed with at least a minimum 5 nodes. But these things are rare. Most issues are found with tiny models, and if you need better assurances, better guarantees, then TLA Plus has a way for you to also write proofs that show that things work for any number of nodes, any number of messages. But it's just more work, more manual work that's involved to show this, that it works for any number. Okay, getting back to where we are right now, we've checked that our spec defines some kind of system, right? We haven't checked anything useful yet about the system. For the moment, we will quickly change our specification and also introduce a new concept in TLA Plus, because so far we defined our specification in a way that all the nodes are active at the beginning and there are no messages pending. That seems a little bit strict, right? Because if we run eventually the algorithm termination detection, the individual nodes might be in any state, right? Some of them might be active, some of them might be inactive, some have messages pending, others don't have messages pending. And we can quickly express this fact by saying initially active is not equal to this particular function, but rewrite what used to be this n in a node, and then here is some true, to this other syntax where we use a different arrow and don't use an iterator here. This is what I called an iterator. And this now defines not just a single function, but the set of all functions mapping from node to Boolean. This gives us all combinations from node to true and false. And I do the same for all combinations from node to the natural numbers. And then we say, in the initial state, active is in these functions and pending is in these other set of functions. And that tells the model checker to pick each one of them, each function, and generate behaviors from these states. So we have now many initial states. How many initial states do we actually have?
Infinite number, I think, because the second is has codomain of natural numbers.
Exactly, right? So this down here, this defines an infinite set of functions going from the set of nodes to all natural numbers. The model checker, if we try to check this, the model checker will just give up right away, right? I'm dead in the water here. You're trying you're giving me a range here or a set that's infinite, that's unbound, and ask me to enumerate it. I won't even start. Okay, but this is what we want to model, right? So again, we're going to move this stuff here, this init function. We're not going to move it, but we're going to redefine it in our MC async termination detection module and say, okay, we're going to check this for 0 to 3 for pending. This active here, that's a Boolean. So this one is a finite set of functions. We will leave it as is, but for the natural numbers, we redefine it. And in the config file, we can just tell the model checker, substitute or replace this init function with this MC init function. We can do this for all other definitions as well. I could have also redefined the set of natural numbers to be the set of natural numbers 0 to 3. And this is also a common thing in TLA plus, that we redefine the natural numbers to some small set. Again, relying on the small scope, small model hypothesis. And now we can again check our model, still get a finite model, some thousand states or so. If you don't get the exact same number of states, perhaps in your workspace, some files, some values, a little bit different, but this should approximately work. Okay. And now let's start something, let's check something about our specification. So far, we haven't checked anything, right? We've just defined a state machine, init and next. We made sure that it's not infinite so that the model checker can enumerate the states, but we haven't learned anything useful. We don't know if this works, if this has anything to do with termination detection. It's just a bunch of formulas. And we're learning TLA plus, right? So we learned TLA plus, but in terms of termination detection, we haven't made a lot of progress yet. So let's state a property or an invariant now that we will call type OK. That's just convention. But I said earlier, TLA plus has no types, and it's very expressive, so it's easy to get some expressions wrong. And I got this expression wrong down here, right? Type -2. And perhaps in a dependently typed programming language, this would have been caught by the compiler. In TLA plus, with TLC and with TLABs, with the proof system, it's common to write this type OK invariant here that says what the valid values are for our variables. And in this particular case, it just so happens, because the spec is tiny, that type OK looks exactly the same as init in this particular commit. Later, this will change. But right now, we can just reuse active and pending as defined in init. And now let's check this model with TLC. And I guess I forgot to, I have to type invariant here, type OK, to have the model check it. And this is what I wanted to get to, right? Now we have a trace here from some initial state where pending is 1. So node number 3 has 1 message pending. All the nodes are inactive. So we started from some in-between state in the computation. All nodes are active, but there's a message pending. This is clearly not a state where implementation would have started with. But our specification allows this. We want it to allow it. So in the successor state, this node is now true. It woke up. But because of my stupid programming or typing mistake, 2 is now at -1. So we get a little bit of type checking back by writing type invariants. So we now know we have to correct this to 1. And then hopefully the model will check out. Yeah, now the model checks, and at least it's type correct. Great. Let's do the next step. This is just wrapping up. So now we know enough of TLA plus, or we've learned enough of TLA plus that we can focus a little bit more on termination detection. As I said, we're going to count messages, and we somehow want to detect termination. This one doesn't detect termination. This just models the set of nodes. So we're going to introduce another variable here that we will actually call termination detected. And this is going to be true if our initiator, our conceptual initiator, would detect termination. So we initialize termination detected to be either false, so the system has either not detected termination, or it's true if this definition here evaluates to true. And for a system to terminate, it means that all nodes are not active or inactive, and there are 0 pending messages. So this here, the terminated, represents the system of nodes having terminated. So if this is true, the system of nodes has terminated. Termination detection, on the other hand, that's a separate thing. That means the algorithm termination detection has detected termination, right? So clearly 2 things: terminated, termination detected. It shows here that in TLA+, things become easy because we can reason at the global level, right? Everything is global. The variables are global, and this is not meant in the context of scopes like in programming languages, but all the information is global. In a distributed system, you couldn't easily write terminated. In a real system, you couldn't write terminated because you would have to talk to each node, right, and find out if it's active or not, and find out how many messages are pending. So then you need something like a consistent snapshot algorithm or something like that. Some heavy machinery to even answer the question whether or not things have terminated, which happens to be exactly what we want to build right now, right? So we have a chicken and egg problem. But here in TLA+, because we specify things at the global level and not at the node local level, by the way, how we model, this becomes easy. This becomes straightforward. We can benefit from it. We can say initially the termination detection has either detected termination, if this happens to be true, or it hasn't. We want to check both cases because detection might happen later. It's been added to the type OK invariant. Now it looks different than the init. And there are 2 cases where termination detected can happen. It can happen if a node terminates, then it might or might not, so it's possible for it to detect termination. Or there's also a separate action now, detect termination, that allows us that if the system has terminated, we can detect termination. And this is essentially, logically, conceptually, our initiator that gets the token back without ever sending a token around, with ever modeling tokens, right? There's a little bit of TLA+ syntax here because I primed the terminated operator. So far, we've only been priming variables, right? It says what the value of the variable in this state is compared to the value of the variable in this other state. It's primed. But we can also, TLA+ also allows us to prime operators. And then what happens is that in this definition of terminated up here, these guys get primed when terminated prime is evaluated. That's nice. And all of the variables are primed. And it even happens so that if I would write a primed operator up here, then it becomes syntactically incorrect. Because now the level checking, the syntax checker tells us, now you double prime things. Double priming doesn't work. We cannot go to from the current state to the successor state of the successor by double priming it. That's not allowed. That's not how it works. And it's even disallowed at the level of the syntax. Okay, we have to remove these primes up here. But we define the value of termination detection, the next state, based on the evaluation of this terminated here, of the prime terminated. And the detect termination detection, detect termination action, that's a lot simpler. That just sets it to true. Okay, we can check this again and see if there are no issues. We stay at 513 states. And now let's check something useful about this property, because now we might want to say, for example, and I will jump one more commit ahead, that should the system terminate, it implies that termination is detected. I think all of you said, or most of you said, you know what implication is. So I don't really have to explain the symbol, this operator here, but I will quickly give you the executive summary. True implies true is equal to true. We can translate this: if it rains, the street is wet. Okay, that's a true statement. The street might be wet even without rain, or somebody spilled a bucket. That's also a valid statement. If there is no rain and the street is not wet, then yeah, everything's okay. But there might be the case that there is rain, but the street is not wet, and this cannot be. Yeah? So this is the truth table of the implication. If the left-hand side, the antecedent, is true, and the consequent has to be true as well. If the antecedent, the left-hand side, is false, then we don't care about the right-hand side. And this is what we write here, right? If termination of the system occurred, then it implies that termination is detected. Let's check this property. So it's wired up in the configuration, property stable. And let's see what TLC has to say about it. It says, something is wrong, there's a violation in the initial states. So what's the problem here? I guess we could remove this from the initial state and check this again. And now everything would be fine. So this was super fast. Let me do this slower. I redefined our MC-init to say termination detected is not false in the initial state, but it's only the value of terminated. And if I change this, our stable property holds. There's a minor subtlety going on here that I have to show you with a different technique. Namely, I'm going to shrink the model now, make it super small to be able to draw the state graph. So dump.atd, 17 states. Close this, close this. And you see these 17 states, 16 of them are grayish. You can't read the labels, it's too small. 16 of them are grayish. Those are initial states. And there's one state down here that's not gray, that's a successor state. And here, pending is 0, 0, active is false, false, and termination detected is false. This violates our stable. But it's not an initial state. And this is why, depending on how I stated my initial predicate, the stable property might or might not be violated. Because what this formula says here, in the initial states, terminated implies termination detection. But this is not what we want to say, right? We want to say that always, in all possible executions of our system, the property is right. So let's draw an execution here. So we have our stable here. So this is stable in the initial state. I believe we'll update soon. And then we take a next step and suddenly not stable. And this is the symbol for not. But our current property is only checked on this initial state. Now we enter the realm of temporal logic, where we say something about all the states of the behavior. And there's an operator for which we can use, which is the box operator in ASCII square brackets, which looks like a box if you squint. And it says in all states of a behavior, not just the initial state, but in all states of the behavior, terminated implies termination detected. Later, we will see why we need to explicitly say box. And now, TLC also actually finds the violation of this property. Yeah? In a state that's not an initial state. That's why we now see two states here. And it says invariant stable is violated. Does anybody know why type OK worked earlier? I mean, type OK showed us a trace. And in some of the successor states, there was a violation of the invariant. I think it was the second state. But there was no box written in front of type OK. Any idea what might be the difference here? The difference is just machinery. Yeah, somebody figured it out, great. So the difference is in the config file, I said type OK is an invariant and stable is a property. And invariants are so common that we have this shorthand here, this optimization of the tool, that you can just write invariant and you save yourself the trouble of typing the box operator. So an invariant is just a property with a box operator in front of it. That's the only difference. But there are reasons where we don't want formulas to be boxed or to require that something is only true, where we want to be able to require that something is only true for initial states, as we will learn later. Okay, this gave us, let's look at the error trace again. This gave us an invariant stable is violated here and a two-state error trace. We could also slightly reformulate and strengthen this property by adding another box in here. It's always the case that if termination is true, it implies that always termination detected. Termination never goes back from true to false once it's true. This is what we're saying here. It will obviously be violated because even the previous invariant was violated. But the point now is that TLC no longer says, oh, here's an invariant violation, but a violation of a temporal property. Yeah, we get a different trace, which shows this strange thing called stuttering that we will see later. Okay, so the tool.
Markus, excuse me, short question. Do I get this right, that without box or diamond in the beginning of the property, it only checks the initial state?
If it's a property, if it's an invariant, then it checks for all the states.
Okay,
exactly.
Thank you. Mm-hmm.
Yeah, we will later get to the point where we should always be suspicious of success and should always try to invalidate our spec to catch these kinds of mistakes. And as I said, I make all the beginner mistakes deliberately for you to see them and to get a deep understanding of the tool. Okay, let's quickly skip over the commits. Okay, getting back to termination detection. What does it mean? We get this counterexample here. Does it mean our idea of counting the in-flight messages is flawed? Our design has already been invalidated and it's back to square one. Nope, that's not the case. I once again made a mistake, and a deliberate mistake here, because our implication here, if you really think about this, is wrong. It's upside down, wrong end of the stick. It's not that if the system is terminated, it implies that we have always termination detection, But the safety property here is that if the system says, the algorithm says, yeah, termination has occurred, if it detects termination, then there really has to be termination. Because that's the correctness of the system, right? So we have to swap those two sides. Termination detected implies terminated. And let's quickly check this. And phew, yeah, we do have a design. Now, so far, we haven't fallen over yet. We're still on track towards EWD 998. Okay, let's see. There is another problem with our specification that we can quickly look at, because, as I said, we now have a design thing. Things seem to be useful. Before I move on, there is a question. Isn't the second box useful here? I would say it's a stronger formulation, right? The system never goes back to no termination. I hope that answers the question.
Actually, we are checking two things here, right? First, that when we detected termination, it's actually terminated. And then that if it is terminated, it will never wake up again. Right, exactly. And it's also, this changes it from being an invariant that can be checked on an individual state to something that can only be checked on a sequence of states, right, on a full behavior. Because going back to false again is something that can only be, makes only sense on a sequence of states. There's some state where it was true and then it goes to false to be violated. It's not something that can be checked as true for an individual state, but for whole behavior. Okay, so we've written a specification, a super tiny specification for a thing that we knew would work. Usually you don't know if things work, you are actually modeling, you're designing something novel. And at some point, the model checker says, everything's fine. And that's great. And then you call it a day, go home, and are proud with yourself. And if I do programming, this is how I program, right? Once the tests are green, I'm done. Well, in TLA plus, there's this advice, be suspicious of success. If something works, it's usually just a coincidence. Let's try to see if this is really the case. So TLC has this useful simulation mode, simulate, num equals 10,000, where it just randomly generates behavior. Oh, that's equals basic. So now I ask TLC, generate 10,000 behaviors of length, by default, I think 1,000 states. And print some statistics. It takes 1 or 2 seconds to generate 10,000 behaviors. There's no guarantee of coverage here, but it's sometimes useful. So let's look at this graph, that the statistics it's generated. And the statistics show us there are transitions from a state that occurred from a detect termination action to terminate. So the system goes from detect termination to terminate. That makes sense. There are also transitions going from terminate to detect termination. The transitions going from detect termination to wake up, and between wake up and terminate. But there's no coverage of the send message action. How can that be? There must clearly something be wrong in our system. I skipped a commit here earlier, so you don't know what's going on. But let's quickly talk about this. I said we have to make the model finite, and at some point I rewrote the state constraint that said at max pending is 3 to there is no transition where the number of pending messages increases. This is another feature of the model checker that's useful. People want to write action constraints,
And we've written one here that essentially says almost the same as our state constraint. We make the model finite by mandating that the number of pending messages doesn't increase. But obviously, unfortunately, it has this undesired and unnoticed side effect that send message actions were blocked. So we obviously have to fix our action constraint here and make it right. We will use a state constraint. This was just me showing off the tool, right? And I once again made a deliberate mistake. So once we reverse this, sorry. Now I think it's changed to state constraint here and this back again. And if we simulate once more, well, I forgot the command line. Simulate num 1000 stats basic. And now I have to reorganize all these multiple windows here, make it large enough. So now we can see that send message action happens. Phew! Always be suspicious of success, try to invalidate your design and use all the tools at your disposal. So there's another way of being suspicious of success, which is writing properties that obviously don't hold. Properties that we know are incorrect, that should be incorrect and that should result in an error trace. And if they don't raise an error trace, well, then something is truly broken. So for example, I could just say that I want all transitions to be terminate transitions. It's obviously, this will obviously be violated, right? But I want to see that it's violated to see that there are terminate actions occurring. I could have made it so that it's a send message action, then we could have skipped the previous state graph thing. But let's now do this for terminate. So I would probably try and write this. There exists an I in node terminate I, and this is always the case. But this is not valid syntax. In TLA plus, this is not right. What I have to do is I have to wrap actions, and this is the error that the tool gives us. A box operator is not followed by an action of the form square A sub V. So it has to be the square thing. So I add squares around it and then sub V. What's sub V? We will talk about it later, what the V part is. Let's from now just make it vars, which is the sequence of active and pending. And now we can check if always every step is a terminate step. Yeah, it's not. Okay, that's no surprise here, right? So there's a wake up step. There's one transition going from an initial state to another state, and it's a wake up step. So our only terminating property is violated. That's what we wanted to assure. Now we know that there are wake up steps. So let's make this right and add a disjunct here. Wake up I. So now I will probably get a counterexample that says, okay, there's a detect termination step that violates this property. Detect termination, I believe. And then if I check this, it would complain about the send message action. So let's also make this true for send message. Or send message I, j. And this should now check and produce no violation. No, it doesn't. Great. Not terribly useful, because if we think about this sub-formula here is just our, what is it? Our next step here. So I might as well replace this with next. So what I'm saying now is, okay, I'm checking the property that there's always a next step, sub vars. Subvars gets translated into or the variables don't change. That's just syntactic sugar for checking always next or vars prime equals vars. Okay, but we write it with the underscore. That's not terribly useful, but it's a build up to how we actually write the temporal formula of our system. Because so far, we've made use of this special config here in TLC that says init is init and next is next. But in TLA plus, a system is actually described as a formula. But init and next, this is configuration. This is not a formula. Instead, there's another syntax here, specification, that we commonly call then spec. And we rewrite this guy here as spec. So this is now the temporal formula that defines our system, except that it's missing the initial states. We now know what the next states look like, but we don't know what the initial states look like. Okay, let's fix it. Init and next states. Always next states. And now, check our, I guess I have to fix the configuration file because only terminating doesn't exist anymore. So I'm going to comment this guy, check this model. And okay, I made no typos, great. We now replace the init and next in the configuration of TLC with this real definition of our system. Before, somebody would have to know TLC, the internals of TLC, to really understand the specification. Most people do, it's good enough. But this is really how what we actually check. And now it also becomes clear why init here and why this termination detection up here in its broken form was not violated by successor state, right? Because if this expression, this property here would be checked for every state, regardless of whether it's prefixed with a box or not, then it would mean that this init here would also apply to every state and not just initial states, right? We only want this formula to apply to initial states. And the nice part of this is now, and I find this beautiful here, is that we might as well write spec to be a property. So spec is now the specification, but it's also a property that we check. Okay, we can all see that that spec doesn't violate spec. But in TLA plus, there is no difference between the system that we describe and the properties it satisfies. It's all the same, and you can put them up on both sides of the formula. What we really check is what the model checker checks if we write property here. It checks if spec, the specification up here, implies stable. And it checks spec implies always type okay. And it checks spec implies spec. Okay, makes sense. This one is useless. We don't have to write it because we know it will work. But this is what we check at the logic level. What the model checker with its machinery does for us by hiding a lot of the detail. This is what we actually do, and both sides are formulas. So we can also write spec implies stable implies spec. Stable probably doesn't imply spec. It will fail. But we could write this because this is syntactically correct. If you think of other formal methods, there's usually a distinction between the program, you have some program, and then you have some other formalism of properties. But you cannot use your program to check a program. And here later we're going to see in the context of refinement where this is super useful, why this is super useful. Okay. We could toy with the subscript vars now, but it's not important at this stage. So let's see, I guess I skipped over a number of commits here. So we now have, okay, I've gone too far. There's another piece of syntax we have to learn, another operator we have to learn. Sometimes you want to say that an action not happens, but is possible, that an action is enabled. So for example, we might want to say that always it's possible to take a wake up action. There exists an I or an N in N node wake up N. This doesn't mean that we extend our state space or we just check in every state we find ourselves in, it's always possible to take a wake up step. It's not true. It's not going to be true. But let's check it anyway. So we get a counter example, and it shows us that after 3 wake-up steps, no wake-up step is possible. Well, we are at a dead end. Makes sense, right? There are no messages pending. Without messages pending, the wake-up action is really not enabled. And we mandated that the wake-up action is always enabled. Okay, we could also use a little bit more syntax. And I'm going to introduce a lot of scaffolding here to get to a bigger point in a few minutes. By not using angel brackets here, but use square brackets around the action to say a wake-up action is always enabled and the variables remain unchanged. So the square angel brackets compared to the square brackets change from or the variables remain unchanged to and the variables change. So this happens to give us the same error trace, because if you think about it, this is also one where not only there is no wake-up step happening, but the variables also don't change. It violates both sides of the implicit conjunct that we don't see here. Yeah, we would have, this is what we've actually written. It's not equals to vox. And this is violated. Okay, let's see. Let's skip again, forward real fast. We need more syntax. We need more syntax. We've learned this syntax now. And okay, now we have to make take a step back and think about what we've done so far. Because now we're going to enter liveness, and some I've heard know about liveness, but what's liveness? Liveness is best explained if we first talk about the properties we've checked so far. We've checked safety properties that say something never goes wrong. We design an airplane, and the safety property for an airplane is it doesn't crash. That's quite useful. I like to be in an airplane that doesn't crash, right? But now I give you an example of my airplane. My airplane is just a toy airplane that never leaves the gate. So is this airplane going to violate its safety property that it never crashes? No, it's fine. So it's a perfect airplane. It never crashes. Awesome. But unfortunately, it's not really useful, right? Because eventually, we want to arrive at our destination. We want to get to this conference, at least after the pandemic. We want to be in person again at conferences. So we have to use planes that actually get somewhere. So we need this other class of properties, not just something bad must never happen, but also something good eventually happens. And this is what's called liveness, a liveness property. In programming, you usually don't state liveness properties. They're kind of implicit. The system eventually does its thing. We don't formally write down what we expect it to do. But in TLA Plus, let's write down, in our spec here, let's write down what we want to eventually happen. And eventually is this thing called diamond operator in temporal logic. So we have the box operator, the square, and now we have the diamond operator that looks like a square that's rotated by 45 degrees. And it says, okay, eventually the variable is true here. Let's just comment this guy here for a second and turn it into true. Okay, so that's obviously not the case. It's not the case that the system eventually terminates. And the error trace, the counterexample that TLC gives us, says that there's an initial state and stuttering. So that's my airplane again, right? That never leaves the gate. Because we haven't really required the system to do anything useful here. We just checked whether or not it arrives at its destination. And the model checker tells us, yeah, no, it doesn't. We can also check this for this other property down here and termination detected. And we get a slightly different counterexample. This is longer, but both of them end in stuttering. And stuttering means the variables don't change anymore. So something good cannot happen. So I talked about this part earlier here, right? So I said we checked that spec implies terminated. This is what we just checked. And it doesn't, so we have to add something to the left-hand side of this implication that says something good is supposed to eventually happen. So we will do it soon, we will do in the real spec, we'll do this here. We'll add some F, some formula F, which we will see in a minute. What could this formula be? Any kind of guesses? While I correct the specification.
Well, maybe at any step, some variable must change, not equal to its previous value, to force changes.
Yeah. Okay, that's an interesting thought. We want to require that the variables change. Well, that would allow behaviors where the variable goes from 0 to 1 to 0 to 1 to 0 to 1 and so on. So that's probably not really the good thing we want to happen. We have to be a little bit more precise in what we want, but we could try to write this down. Always eventually some step should be taken. I guess there's somebody who's a little bit familiar with TLA plus and is a few steps ahead of us. Well, for now, I will just, on the left-hand side of this implication, we'll just say, okay, eventually I want the system to terminate it, for terminated to be true and termination detected to also be true. That looks strange, right? Now we have eventually terminated and eventually terminated detected on the left-hand side of the implication and on the right-hand side. And unsurprisingly, now the system does exactly what it should. Yeah, it eventually terminates.
But it's awesome. Cheating. We just require the system to do what we want.
Right, we cheated, exactly. And it's also not very clever. It's not very clever because there's a problem with this. The problem is the scheduler that we eventually implement, whenever it decides to create the next step, to do the next schedule, the next step in the schedule, it has to know whether further down the road this schedule is going to lead to termination. If not, it has to discard this schedule, this prefix of a schedule, and try another one, right? So essentially, our scheduler has to generate all the behaviors, just keep those that end in termination, and then only allow those. This is a highly inefficient scheduler. But we can write these specifications if we want to, if it's useful for the user to see. In the theory book, they are called non-machine closed specifications, and we'll soon see how we write a specification that is also implementable. But the math of TLA Plus allows us to write any kind of liveness properties and conjoin them and add them to the behaviors. What happens here is, if you think about this part of the spec, this formula is, if you another representation, another mental model for it is that it defines a set of behaviors. There are many, many behaviors described by this formula here. They are all infinite behaviors, but it's a set of all of these infinite behaviors. And by adding logical ending, conjoining these formulas here, terminated and termination detected, we are going to remove behaviors from this set of behaviors. They are gone, so suddenly we're on a smaller set. And this is what makes what's also another way of saying that this is not a machine closed specification. We want to write something here, some F, that guarantees that our system makes progress without ruling out any kinds of legal behaviors of the system. I will be back in a second. There was some background noise. Sorry about that. Okay, so let's write an F here. F equal, capital F equals, and now something. So we've learned all of this now, but this is now a bigger formula I'm just going to introduce. So eventually, oh, and one thing I haven't noticed yet. So we learned about box, right? We also learned about eventually now. So we have two temporal operators. We've seen them individually. But what we can do is we can also combine them into, always eventually, and into eventually always. That's also okay, and then some P, right? Some P, some Q. Let's quickly create a mental model for this. Okay, so we have diamond box P, and we have box diamond P. And now we have our computation here. And I will just sketch out a few behaviors that violate or don't violate this formula. So here we have a P and not P and not P and a P and a P ad infinitum. So this behavior that satisfies the first formula. Eventually always P. There is some prefix of this behavior, some finite prefix where P might or might not be true, but at some point there's a suffix from which on P will always and for the entirety of time will be true. The box diamond, the always eventually P, that's not P, 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 not P, P. And I can't really draw this as a continuous line. I have to loop this around. So let's suppose this extends into a not P. And now I continue this behavior by introducing the cycle. So now there is a cycle where P will always eventually be true, will repeatedly be true. And this is what we can express by combining box and diamond. And those are the only two operators in TLA+. And as a matter of fact, the box diamond operator is equivalent to not, the diamond operator is equivalent to not always not P. So there's actually just one operator in TLA+, which is the box operator, and everything else is derived from it. Again, I find this beautiful. I find this very elegant. So what do we make with it? So what is the usefulness of box diamond? Okay, good question. Let me answer it now. So, and I frequently get this wrong. So should at some point, so now we're talking about the liveness property that our system should fulfill. Eventually, always, some action, let it be the next action, is enabled. So there is a point from which on the next action can always be taken. There might be a prefix where it cannot be taken, it's not enabled, but there might be a point where it's enabled. Then it applies that always eventually a next step occurs. So what we're saying now is, if it's always possible at some point to do a next step, well, then infinitely many of those next steps happen. It's quite involved, right? We will get to a shorthand in a minute, but I really wanted for you to see this, to see how this formula comes to be. So we check this and we see something has changed, right? It no longer ends in stuttering. We now get a lasso, a counterexample that has the shape of a lasso. So there's a loop where something never becomes true. We're still checking the two temporal properties, eventual terminated and eventual termination detected. And here we get a counterexample that says, yeah, it's possible for two nodes or n nodes to simply keep exchanging messages and never terminate. No? Okay, that's fine, right? From the specification, that's fine. So this is something we perhaps might or might not want to address. I don't know. But we've taken care of the stuttering. We've defined that the system, what the system has to do, if it's possible that it does so, by stating this strange formula F here. It's really long and complicated. And because it's so long and complicated, there's a shorthand for it that is weak WF underscore the vars, the variables, and the action. So now we have a concise way of writing this long formula. We can just inline it down here to make it more readable. And we say we want weak fairness on the next state relation. Weak fairness indicates that there is also something like strong fairness. We won't need it here. It's less common to use strong fairness. But the important point is the way how we stated this fairness property, we are guaranteed, and there's a paper where there's a proof that this is guaranteed to be a specification that's also implementable, because we've only said at the level of the actions in the specification and the variables, what kind of liveness, fairness we expect. And this doesn't rule out any behavior that's allowed by this subformula here at the beginning. Quite nice. Okay, so much about fairness. We still have this problem to deal with, right? So we've written a specification. We know that they can indefinitely keep sending messages. And if we think about this, then we also realize that this is something we want to allow. We want to allow the system to keep sending messages because we only want to detect termination if there is termination, but we don't want to mandate termination. Just because we don't want our termination detection algorithm to require of the system for which it detects termination that this system always terminates. That wouldn't be a useful algorithm, right? Because we might want to use it on systems that in some cases don't terminate. So we have to deal with this issue here. Any ideas what to do. Oh, there's a quick question. Why do we need the angel A sub vars here? So that goes back to the fairness part. So why in the fairness, why do the vars appear here? And let me, let's see, can I get this formula back? Yes. Why not just enabled next, I guess. Token, maybe we need to introduce it. That's the next question. So why don't we just do this next here? Or do perhaps this here? This is, or the vars remain unchanged, right? So that would allow for variables to be unchanged. Okay, there's another question. We need to introduce a token in our spec. So that's the way out for the problem we have. Let's see how. Let me get rid of this here. Let me replace this with vars and next. Can we get a good fix this problem by introducing a token? Nope, that's perhaps one way, but we don't have a lot of time anymore, so we won't be able to deal with tokens anymore today. But we have to go back and think one more time about our properties here. Terminated, eventually terminated, and eventually termination detected. Overall, quick side note, the most powerful tool when you work with TLA Plus is your brain, right? TLA Plus is not this magic box that you click, where you press a button and it gives you the answer, yes, this thing works. It's just this brain extension that helps you keep track of more than 7 variables. It makes you a better thinker, but it doesn't free you from thinking. So we still have to think what's going on here. But the point is we get deep, deep insight into what seemingly from the outside looks like a simple problem. But now we see that with liveness, things are super complicated, right? In an implementation where you just keep generating behaviors, you usually don't notice these liveness issues. Due to probability and long enough runtimes, eventually some action will probably be taken. But this might burn a lot of compute cycles or might take a very long time. And there are also always cases where this doesn't really happen. But my assumption is that if there are liveness issues in implementations, we usually fix them by poking the machine, by restarting the machine. We never really understand what's going on really in the inside. And here we have a first-class mechanism to talk about liveness. But getting back to this particular specification here, the real problem is, well, our liveness properties are too strong because we mandate that the system eventually terminates. This is not what we want to say. Let's get rid of this guy here and compress it into a single one. Because what we actually want to say is that always it's the case that if the system terminates, and only if the system terminates, then eventually termination is detected. So now the behavior where termination never occurs, it's a valid behavior for our system. It won't violate this property here, I hope. Let's find out. Yeah, it does. So it seems we really got ourselves here a real system specification. This is a common property. Always terminated implies eventually something else. But there's yet again syntactic sugar in TLA plus, so we can write terminated, and then this wiggly arrow here, termination detected. Now this is the same as in it's equivalent to the previous formula with a box and the eventual, just a shorthand with a wiggly arrow. And it's called not wiggly arrow, but leads to. So terminated leads to eventually termination detected. We could also strengthen it again. And here we are at a system that seems to more or less work. Awesome. I think that also kind of addresses both of the last two questions in the chat. I think we are running out of time for today. I think I'm very happy with the outcome of today, of what we've covered. Let's use the remaining few minutes to recap what we've done today. I know this was a lot of content. This was a lot of content, and you all deserve a pat on your back, because essentially we covered now the difficult parts of TLA+. The TLA and TLA+, the logic, the temporal part of TLA+. And we are done. We happen to be done with part A of the tutorial. There is a part B, part C, part D, part E. There's way more content than can possibly fit into 5 hours and that can possibly be learned within a few days. But we really have seen, we've climbed the mountain. We're at the top of temporal logic mountain, and we now look down, and tomorrow can really look more at the modeling of EWD 998 with TLA+, experience a little bit more about the tools. We can perhaps look at the proof system and look at the symbolic model checker as a tool outlook, but beware, writing proofs, that's a different chapter. There's a different book next to specifying systems that just talks about proofs, and proofs are not cheap. I wouldn't say they're expensive, but they don't come for free. With a model checker, we have the luxury that we don't need to know why our specification works. Yeah, it just works, and the model checker confirms it for us for some finite model. That's great, that's useful, right? And this is what you do with model checking. You keep checking your model and try to invalidate your model until your model checker runs out of time or says, yeah, things are fine. But you don't need deep, intimate knowledge why things work. If you want to write a proof or give an argument to the computer why your algorithm works, then you have to give the computer the argument, and the computer will tell you your argument is right or wrong. But you need to know why it works. So that's why it's better just to give an outlook. But tomorrow we are really just, as I said, simulate real modeling. We want to wrap up EWD 998. We have to learn about records, if then else, and the choose operator. But the really interesting part in my perspective is the refinement. Okay, there's other questions, general questions. It says 1 minute, 20 seconds left. Please ask questions. And we can also leave the chat open for half an hour or so. I'm happy to leave the Zoom thing open to answer more questions after the official conference does today's wrap up. So I will stay in the Zoom call and happy to answer more questions. There's one in the chat. Is writing a proof in TLA plus more effort than writing a formal proof in English? I would say no. There's one concept is, so for a proof on paper, you also need to know why things work. And this is the hard part in writing a proof. Afterwards, you want to convince the proof system that your reasoning is sound. And sometimes proof systems are surprisingly stupid. And you have to break things down to a very trivial level, seemingly trivial level from the perspective of a human. But in TLA Plus, you can always say, this is so easy, I don't need to further prove this with the proof system. I can just see that this is right. So I omit this proof obligation. It's a hierarchical proof in TLA Plus, and then some sub-goal can just be omitted. And you don't have to bother with convincing some backend prover. Okay, I guess we are
set. Yes. Hi, everyone, once again. And Markus, you're great. You're finished right in time, second to second. Second, thank you for your very inspiring and informative second part and first one on TLA Plus. I think you're doing a very important job, and I am sure that we will rewatch your session a couple of times after conference to learn everything that you're talking about. And yeah, I'm saying goodbye to you for today, and we will look. I will meet you tomorrow on a continuation of your workshop. Goodbye, Markus.
Okay, bye-bye. Thank you.
Bye bye. See you tomorrow.